All right. So today I'm going to talk about the effect of chemical properties on on liposomal encapsulation of radiopharmaceutical tracers. So that study was performed by me, Professor Yasser, and Adala Al-Hambali. We were trying to encapsulate the radiopharmaceutical tracers and the liposomal agent to reduce the toxicity effect, to enhance the stability, the biodistribution, the pharmacokinetics of the tracer and the radio isotope itself. So in brief, let's talk about the liposome. Liposome is a closed spherical lipid bilayer which forms an internal cavity capable of carrying aqueous solutions. A lipid bilayer is composed of two sheets of tightly arranged phospholipids. These molecules have a hydrophobic tail and hydrophilic head region. Drugs are being developed which have a liposome delivery method due to the structural versatility, compatibility, and biodegradability, non-toxic, and non-immunogenicity nature. The selection of phospholipids and the ratio of liposomes components are important to determine safety, stability, and efficiency of liposomes. The ability of liposomes as drug delivery system can be affected by the number, rigidity of the lipid bilayers, size, surface charge, lipid organization, and surface modification. And in that research, we always concentrating on many factors like the surface charge, like the size of the liposomes, as well as having some chelators. We didn't apply PEG, but probably we will do it for the next few days. However, we tried cholesterol, and we'll talk about the effect. Liposome components and properties. The main component of liposomes are glycerophospholipids, which are amphiphilic lipids composed of glycerol molecules bound to phosphate groups and two fatty acid chains that may be saturated or unsaturated. The phosphate group can be also bind to another organic molecules. According to the organic molecule, natural phospholipids are classified as PA or phosphatidylcholine or PE, PI, PG, and phosphatidylserine. Liposomes are formed by self-assembly of natural phospholipids or synthetic. Main sources of natural phospholipids are egg yolk or soybean, for example, phosphatidylcholine or phosphatidylethanolamine. These are another examples of synthetic phospholipid. We use the SPC, we use the OPC, DPPC. We went through that. We'll go through that later. The types of interactions that forms liposomes. During the formation of the liposome, there are three main interactions: hydrophilic interaction between polar head groups, van der Waals forces between hydrocarbon chains, hydrogen bond with water molecules. Liposomes are classified either to single or multiple lipid bilayer, depending on the number of phospholipids layer. Liposome can be positive, negative, neutral charge, depending on the head of the phospholipid, and we can use like particles for that, cationic or whatever. Phospholipid with longer saturated hydrocarbon chains have higher ability to interact either by forming rigidity in order to have ordered bilayer structures. The stability of liposomes can be enhanced using phospholipid with longer tails, low degree of tail, unsaturated, and ether linkage. Also, to enhance the stability of the liposome, we use cholesterol like the one we use in that research, polyethylene glycol, just to form the steel liposome, and polymers as a chitosan. However, they can affect the immune system. Liposome structure modification, the cholesterol mainly, the presence of the cholesterol in the lipid bilayer of liposomes can influence the bilayer fluidity and the rigidity. This will result in permeability reduction, so the half-life of the drug encapsulated would be even longer, and increase the stability. The cholesterol function, when the cholesterol embedded in the bilayer, lipid bilayer, reduces the molecular mobility of the bilayer, thus regulate the fluidity and the permeability as well. If there is no cholesterol, liposomes interaction, the liposome will interact with the protein, and that will reduce the performance of that drug delivery system. Glycerol also could be used, chitosan. Yeah, now we're moving to the transition temperature. The transition temperature is the temperature at which the phospholipid transit from gel to liquid crystalline phase. Transition temperature depends on the length of the fatty acid chains, degree of saturation of the hydrocarbon chains, ionic strength of this suspension medium, and the nature of the polar head group. If the temperature is lower than the transition temperature, we can see that the phospholipids are in gel phase, low fluidity and low permeability. Molecules within bilayers move gently. If the temperature is higher than the transition temperature, phospholipids are in liquid crystalline phase. There will be high fluidity, low permeability. Molecules within the lipid bilayer move quickly. In case the temperature is almost equal to the transition temperature, the permeability increases significantly. Based on the number of the lipid bilayer, we can classify the liposome to unilamellar and multilamellar vesicles and multivesicular. And you can see the types of the liposome according to the lamellae. Also, we can classify it. It's according to the vesicle size. We can see that the recent vesicle type formulation is the multi-compartment liposomes. It's composed of two different types of vesicle connected through a tight bilayer interface. How to prepare liposomes? We have many methods to prepare liposomes. Passive loading techniques, active loading techniques, mechanical dispersion method. Actually, the most used method is the lipid film. And also we use desonication, extrusion, and the membrane extrusion as well to minimize the size of the liposomes. The thin film hydration is the most used method. Depending on the hydration condition, this method can create liposome with different structural organization. However, the disadvantage production of larger and heterogeneous liposomes, low entrapment ability, difficult to complete removal of the organic solvent. That's another technique, the reverse phase evaporation. It takes really long time to prepare. Solvent injection technique. It's quite good technique to use. However, the liposome sizes, you'll find many liposome sizes, uni and multilamellar. Detergent removal technique. The main disadvantage is the impurity, as long as we're using many detergent in that technique. In the size reduction technique, we use sonication. Sonication bath or a probe. Personally, I prefer bath as the probe is could produce some toxic effect from the probe tip. Homogenization, also following the sonication process, and extrusion. After preparation of the liposome, the drug loading method takes place. Positive method, or passive or active. So phospholipid are major structural component of liposomes. The most common phospholipid, as we said, is phosphatidylcholine. Its amphiphilic molecule consists of hydrophilic head and also it contains a glycerol bridge. As we can see here, the cholesterol as well. PEG is really interesting to use with the liposome. So in our study, we used DPPC to produce liposomes. An active loading method mediated by sulfate gradient is included in that protocol. 200 nano of nanoparticle was prepared. In that method, we use the sulfate gradient, and we find that with the sulfate, we got the lowest, the smallest number of, the smallest size of the nanoparticles comparing to the ammonium sulfate. So nanoparticles improve the uptake and stability of the drug, as well as the toxicity. We also compared the tracer itself without encapsulating it within a nanoparticle effect, toxic effect, and when it was capsulated, there was a huge depression in the toxicity effect. By using ammonium sulfate, the size of the nanoparticle has been reduced to half comparing to other buffers. When drug was encapsulated into nanoparticles using ammonium sulfate gradient loading technique, the concentration of the drug, as well as the half-life increased. As you can see here, it was the size before using the ammonium sulfate was above 1,000, and then it was slightly getting closer to the 100, and then we reached 200. The stability of ammonium ion gradient is related to low permeability, the sulfate, which also stabilize and accumulate for prolonged storing period. As we said, it increases the half-life of the drug, as well as the circulation time, the biodistribution, of course, the effect of the drug uptake is getting higher. So thank you for listening. Any questions so far?
Any questions from the participants?
Thank you so much for listening, and I would like to thank the organization committee for that great responses and organization. Thank you so much.